Bolzano-Weierstrass theorem, and he said actually this is an important result. This is very important, as I told you. It can be regarded as the backbone of analysis even, because eventually functions, everything is a limit. This talks about limit, no? Bolzano-Weierstrass theorem. Let's see how we prove. Let A and B a bounded sequence. Then it has at least one subsequence which converges. It's a very important one. But in this proof, by studying this proof, you will not learn how to find it. It is a result. If it is bounded, you know there exists a subsequence. No, that's why I told you maths is difficult because of the implication, and they are existing. Because to me, those who are not doing mathematics, bioscience, medicine, engineering, this kind of people, what is this? Where is it? They want to know physically. No? But what is the first term of that sequence? They ask. How do we know? All we know is there is a sequence. It is like that. Very important, however, you need to remember that, like you remember Pythagoras theorem or midpoint theorem. Midpoint theorem is not used, by the way. But Pythagoras theorem, Hilbert spaces means where Pythagoras theorem is valid. This is infinite dimensional, thing for Pythagoras. Yeah. Anyway, so let's prove it. He says let L be the limit superior. Since it is bounded, we know that lim sup is a real number. So he says let L. Since we have A and B between minus m and plus m, for all natural numbers n, it follows from the comparison principle whatever, lim sup is also in between minus m and plus m. Right? In particular, L is a real number and not plus infinity and minus infinity. By proposition 6.4.12c, L is thus a limit point of n equals 0 to infinity. Right? Thus by proposition 6.6.6, whatever it is above, there is a subsequence of A n going 0 to infinity, which converges. What he says is he takes the lim sup. If the sequence is bounded by minus m and capital M, lim sup is also in between minus m and plus m. However, lim sup it doesn't have to be a limit, but it is a limit point. We studied that. So that means there is a sequence whose limit is that number, whatever it is, no limit, L, capital L. So there is now you began from a sequence, now you have a subsequence which converges to the lim sup. Now if you take the subsequence as a sequence, new sequence, so that is a sequence which converges to lim sup. That's what that is what is the proof. But after this thing is over, if we can find time, as he said that he will go to Prabhat, we can prove it in a different way. You follow the proof?
Yeah.
Though he took lim sup here, he could have taken lim inf also. Same thing. Because you are given a sequence, every term is in between minus m and plus m, then you know it has a lim sup. Lim sup is a limit point, but then by taking limit point you can have a subsequence which converges to L. That is his proof. But this is not how, this is correct actually. This is not how I proved in the books that I have written, although this is correct. But you need to remember this thing. It's good that if you can remember the proof also, not line by line. By remembering, try to remember in proofs, you are not going to get anywhere. That will kill you, time also. So it is a very, very important result. Every bounded sequence has a convergent subsequence. So we are done with this. Let's see what he says now. The Bolzano-Weierstrass theorem says that if a sequence is bounded, then eventually it has no choice but to converge in some places. Actually, but it has no room to spread out and stop itself from acquiring limit points. Because somebody, if you have, what is it? If the terms are, since the terms are in between minus m and plus m, somebody may try to think of constructing a sequence, I mean, between minus m and plus m. It does not, I mean, it will not have values close to. Somebody can think, no, now this one says it has a subsequence which converges. But somebody who can't think of some, somebody who doesn't know analysis, to construct a sequence that terms don't get closer to each other that much. But he says it cannot be done. No, that's what the Bolzano-Weierstrass theorem says, no. Regardless of how you try, some subsequence, regardless of the way you have constructed the sequence, definitely some subsequence converges. That's what it says. We cannot do it. We cannot write a bounded sequence which does not have a convergent subsequence. That is the strength of the theorem. It is not true for unbounded sequences, he says. For instance, the sequence 1, 2, 3 has no convergent subsequence whatsoever. In the language of topology, so I am not going to comment, doesn't matter. This means that the interval minus m to plus m is compact. You don't know these words, so I am not going to read. I didn't read it. So we finished the chapter here. About Lim-Sup, Lim-Min and subsequences. So now you have to have a good idea if you are not sure of proving this thing on the what page? On pages 6.4.12. Prove it very carefully. You have to really understand it. If you don't understand, you need to ask me. Again, the proof of that every co-sequence converges. That is also a very important thing in analysis. These two. Again, evaluating, when it comes to evaluating limits, 6.5.2, you must know absolutely well. Actually, this is used in A level also. My time, if you take a geometric series A x to the n, first term is ax, next one is ax square, next term is ax cube. Like that series converges if and only if, maybe I am wrong, if mod x less than 1, it converges. So that when I was doing A level, that time geometric convergence of that comes in A level papers also. Now, they are deleting as much as possible. So it is a very important result. Theorem 6.5.3 is very important for you when you are going to construct different kind of sequences, convergent sequences. Sorry, very important. So this pages, because he is concerned about analysis, this zero test, that's also important. But let's say Lim-Sup, Lim-Min chapter, you must be an expert. 6.4, then you get 6.4, 4.11, then you come to 6.5, some standard ones, then subsequences 6.6. If you have any doubts about 6.4, 6.5, 6.6, you have to ask me, because these are absolutely important. And try to get the picture always from a graph or something. The way I explain lim-sup and lim-min, that is very, very important, because the proof is in the picture. You cannot, even when you are doing a O-level geometry problem, you cannot say, refer to the picture that you have drawn. You need to prove O-level geometry theorems or solve O-level geometry problems without referring to a picture, because if you have drawn a wrong picture. Yeah, very important. But to get the motivation, pictures are very important. Or you say, if you think that I am a very mean, nasty person, you find it difficult to learn from me. No? Oh, Ram Singh is a very nasty person. So if you are thinking of becoming a professor, you have to be somewhat likable person. Because otherwise, if students don't like you, you don't enjoy teaching. You should be attracted by the student when you become a teacher. Because then teaching maths, especially analysis, very entertaining. Very entertaining. So now we are going to go to the last thing, real exponentiation part 2. As I told you again, be an expert in these three sections, that 6.4, 6.5, 6.6. 6.7 is just a definition. Sooner or later you will also begin to think like this. But instead, let's go through. We finally return to the topic of exponentiation of real numbers. I told you now, so if somebody asks you 5 to the 3, you can say 5 times 5 times 5. If you ask somebody 5 to the 1/3, you can say that is a real number x, x to the 3 is 5. But if somebody asks me, not you, say what is the meaning of 5 to the square root of 2? I don't have a reply. But I do have a reply if analysis students ask me. That's what this section is about. Okay, so in fact, we define x to the cube for all rational cube and positive real numbers x. X to the cube was defined, but we have not yet defined x to the alpha, when alpha is real. We now rectify the situation using limits in similar way as to how we define all the other standard operations on the real numbers. First we need the lemma. He says, continuity of exponentiation, let x greater than 0 and let alpha be a real number. This is not on the board. This is natural, this section, but of course we have to justify many things. Okay, right. Let x greater than 0 and here he said let alpha be a real number. Let q and n going 1 to infinity be any sequence of rational numbers converging to alpha. Qn is a rational number, Qn converges to alpha. Then x to the Qn, n going 1 to infinity, is also a convergent sequence. Furthermore, if Q dash n going 1 to is another sequence of rational numbers converging to alpha, then x raised to the power Qn dash has the same limit as x to the Qn n going 1 to infinity. What he says is that now we are trying to define x raised to the power alpha, where alpha is a real number. So alpha can be square root of 2. So you don't know And I don't know, actually also, to tell a normal person what is the meaning of, as I told you, 5 square, 5 to the root 2. I don't know, but I can tell you. So what we do is, we take a rational sequence Qn, n going on to infinity such that Qn converges to alpha. You are given that alpha, assume it is irrational, for instance. So you want to define x to the alpha. So what you do is, you take a sequence of rational numbers, these are rational. This limit of this thing is alpha. So I want to say x to the alpha means x raised to the power limit of. No, sorry, I am writing wrong. X to the Qn. Limit n tends to infinity. This is what I want to say. Since Qn converges to alpha, so it's kind of at home, no? I mean, you kind of agree. But there is a question. If you take another one, Qn dash, again n going on to infinity, that's that this thing, then whether he will get a different limit. You see what I'm trying to say? Because I want to say x to the alpha is limit n tends to infinity x to the Qn. So, since you two are different, you may choose one sequence, I choose another one. So, if I were, then we have a question, limit n to the alpha, and n tends to infinity, x to the Qn dash. Are they same? Are they the same? If so, only we can define this way. So that's what he is going to prove here. This is x to the Qn when you take n tends to infinity, x to the Qn dash, both are equal. Since both are equal, I can say x to the alpha is that. That's how we define x to the alpha, when alpha is not rational. Even if alpha is rational, this is correct. But that is the definition. That's why I told you, if you ask me what is the meaning of 5 to the root 2, I can tell you. It's, however, artificial definition. X to the 3, not artificial, no. You write x times x times x. X to the 1/3 also is not artificial, somewhat, of course. Not straightforward. 5 to the 1/3 is a real number x, such that x to the 3 is 5. However, x to the alpha, if alpha is an irrational number, there is, you cannot say that way. You can say multiply x alpha times. Oh, you cannot say find a y raised to the power 1 over alpha is x. We don't know. We cannot say that. So, this is the meaning. This is how we define. You take, if alpha is a irrational number, you take a sequence of rational numbers which converges to alpha. Then you define x to the alpha as limit n tends to infinity x to the Qn. Because we have defined real numbers raised to the power rational numbers. We have defined. So then there is a question before defining that way. If you take another sequence of rational numbers which converges to alpha, you get the same thing. If you are not getting the same thing, you cannot define. You understand? So he is saying these two limits are the same. Proof is not. He has wrote it here up. It's longer than the Ohio read. It goes for. But this is not difficult. Let's go through it because without writing on the board, let's go through it. There are 3 cases: x less than 1, equal 1, greater than 1. So proof definition is for all real numbers right away if x is supposed to be a real number. But the proof has 3 cases. Do you agree that this is a reasonable definition? You cannot define x to the alpha in a sensible way, but if you take the sequence of rational numbers which converges to alpha, then by saying this way, x to the alpha is limit n tends to infinity, x to the qn, if it has a limit. Is it fair according to you? I mean, what do you think? So, we always do this sort of thing in analysis. Always do. So, however, to define this way, 6.7.1, well, it's a lemma. Lemma is very important. Regardless of the rational sequence you choose, then it takes x to the qn and take the limit. Limits are the same. You may have different sequences, but converge to the same thing. Okay, there are three cases. He said x equals 1 is rather easy, because when x to the q is 1, if x is 1, 1 raised to the power q is always 1. So we shall just do the case x greater than 1 and leave the case x less than 1, which is similar to the reader. So he is doing only one part, x greater than 1 case. I think so. It is a proof goes to one page, but we can understand the proof, so I will go through it. No need to write now. This is the book. Now you need to remember this thing. When you become an analyst, you do in your all the things like this. When there is no meaning, then you think, oh, this is the way to do it. So mathematicians are like that. Both of you can become mathematicians, but just because of you are good, you cannot do it. You have to work very hard, quite a lot of work. But it will be a lot of fun, unlike in other subjects. You know, as people, they are having fun. So in USA, whenever I visited, when I was there, I would visit American homes in vacations. Oh, genius! They didn't know that I was saying very hard time. But they say, oh, genius. Because people in the world are scared of mathematics. Actually, mathematics is the only admittedly difficult subject. Because you have to think. So that impression is not given by A-level maths. That's the thing I am concerned. I don't like it. Okay, let's go. Let us prove that x to the qn n going 1 to infinity converges. First thing is that no. By proposition 6.4.18, it is enough to show that x to the qn is a Cauchy sequence. Every Cauchy sequence converges. To do this, we need to eliminate the distance between xqn. I can estimate. We need to estimate. I will look at here. xqn and xqm. Let us say that further. So we are going to prove that x to the qn is a Cauchy sequence. In other words, we want to prove that far away distance between x to the qn and x to the qm are as close as we like. That's what it says. Okay, let us say for the time being qn greater than or equal to qm. Therefore, x to the qn greater than or equal to x to the qm. That is because x greater than 1. You have proved it. So, distance between x to the qn and qm is, of course, x to the qn minus x to the qm, since qn greater than qm. Then you can pull out x to the qm out, because qm is the smaller one. Then you get within parentheses x to the qn minus qm, whole thing minus 1. Since qn n going 1 to infinity is a convergent sequence, it has some upper bound capital M. Since x greater than 1, we have x to the qn less than or equal to x to the qm, right? Any qn is less than or equal to m. X is greater than 1 case. I hope, yeah, you are at the case x greater than 1. So certainly x greater than 0. So you have x to the qn less than or equal to x to the m. Thus dx xqn comma xqm is mod of x to the qn minus xqm. Now you have pulled out x to the qm now out. So that thing is less than or equal to x to the m times x to the qm minus 1. Up to that point clear, no? Now let epsilon greater than 0. We know from by lemma 6.5.3, whatever it is, that the sequence x to the 1 over k going 1 to infinity, is eventually epsilon x to the minus m close to 1. Eventually. Because we proved that x to the 1 over k converges to 1. No? We proved it, no? I mean, we didn't prove, but it was 6.5.3 is about that.
Converges to 0.
Converges to 1. X to the converges to 1. X to the 1 over n converges to 1 if x is positive. Without somebody who does not know mathematics will say n tends to infinity, 1 over n tends to 0, therefore x to the 0 is 1. That is kind of a proof, but we cannot do it. We have to prove it. Very sharp. So dxqn xqm less than or equal to x to the capital M times this thing. So we say we know that x to the 1 over k going 1 to infinity converges to 1. Therefore, there is a time at which x to the, thus there exists k greater than or equal to 1 such that x to the 1 over k minus 1 is less than or equal to any epsilon. We have x is fixed for this problem. It's the given number. Epsilon is we have fixed. It is arbitrary epsilon for the time being. Epsilon is positive but arbitrarily fixed. Therefore, this thing is less than or equal to epsilon times x to the minus m. Is it very clear, or do you want me to write it on the board?
Clear.
On the board?
No, it's clear.
It is clear, no? Now, Qn is a convergent sequence. It is clearly Cauchy, and so there exists an n greater than or equal to 1 such that Qn Qm are 1 over k close for all nm greater than n. So what it means is Qn minus Qm in absolute value less than or equal to 1 over k for any nm greater than some integer n, because it is Cauchy. No? Thus we have dxn xqm is equal to x to the n. That is not true. It's less than, no? This equal sign should be replaced by less than or equal sign. Do you see that?
Yeah. Above one is that.
Here
it says exactly the same one.
Equals x to the m or less than or equal to x
Less
to the
than
m.
equal to.
Then we should buy his book.
No. No, sir. I mean the exact same one is written as the
On the
less
top
than
he
like-
says the less than or equal mark on the top.
Right. Okay, less than or equal to x to the m times, within parentheses, x to the qn minus qm minus 1 on the board also. So what I said was, this must be less than or equal, that's what I mean. No? So because now this n and m are greater than capital N, therefore he can replace x to the 1 over k by qn minus qm less than or qn minus qm is positive, and qn minus qm less than 1 over k, because our capital N is, n and m, simple n and simple m are greater than capital N. So we get then x to the m times x to the 1 over k minus 1. When you multiply, you get x to the 1 over k minus 1 is less than or equal to epsilon times x to the minus m. So he is replacing that. Then you get less than or equal to x to the capital M times x to the epsilon times x to the minus m, which is epsilon. So what he has done here is, he has shown that distance between x to the qn and x to the qm is less than epsilon. That's what he has proved. Now, for every nm greater than or equal n such that qn greater than or equal to qm, by symmetry you also have this bound when nm greater than or equal to n and qn less than or equal to qm, you get the same thing because distance, same domain. Thus the sequence x to the qn n going on to infinity is epsilon is steady. Thus the sequence x to the qm n going on to infinity is eventually epsilon is steady for every epsilon greater than 0. That is also true. And thus a Cauchy sequence as desired. This proves the convergence of x to the qn n going on to infinity. Actually, this is a proof you would have written if the proof is not given, if the proof is not given to you, you would have produced this proof. It's not sort of natural thinking. There is no big trick here. Nothing. This usual writing. Now we prove the second claim. It will suffice to show that x to n limit n tends to infinity, x to the qn minus qn dash is equal to 1. This is the second claim. So let's see. Since the claim would then follow from limit loss x to the qn is equal to x to the qn minus qn dash times x to the qn dash, because that is, if the limit of x to the qn minus qn dash is equal to 1, then you will get x to the qn is equal to x to the qn minus qm dash times x to the qn dash. So then you get x to the limit of x to the qn and limit of x to the qn dash are the same. Do you see that?
Yeah.
So he says write Rn is equal to qn minus qn dash. By limit loss we know that Rn is Rn converges to 0 because qn converges to alpha, qn dash also converges to alpha. Not the alpha, what is the term here? Alpha, no?
Yeah.
So then qn minus qn dash converges to 0. We have to show that for every epsilon greater than 0, the sequence x to the Rn is eventually epsilon close to 1. That's what we want to do. But from lemma 6.5.3, we know that the sequence x to the 1 over k is eventually epsilon close to 1. We know that. That's why I told you it is important one. Since limit of k tends to infinity, x to the minus 1 over k is also equal to 1 by lemma 6.5.3. Same thing, because in one place he may be using x, in the other one he may be using 1 over x. We know that limit of x to the minus k going 1 to infinity is also eventually epsilon close to 1. Thus we can find capital K such that x to the 1 over k and x to the minus 1 over k are both close to 1. But since Rn converges to 0, it is eventually 1 over k epsilon close to 0. So that Rn lies between minus 1 over k and plus 1 over k. So from there everything follows. Then x to the minus 1 over k less than or equal to x to the Rn less than or equal to x to the 1 over k. In particular, x to the Rn is also eventually epsilon close to 1. So this proof is, though it is one page, it's normal proof. Nothing he has taken from outside. Go through one more time, you will see it is easy, but it's kind of funny writing. But you have to follow this. At the very beginning, he took x to the qm out. Then he was considering x to the qn minus qm. This, you cannot change that in any proof. This method is should be followed. Yeah. Anything not clear?
No.
It's a natural definition. So now, if you have, if you take two different sequences of qn and qn dash, such that limit of qn is equal to alpha, then x to the alpha and no sorry x to the qn limit n tends to infinity and x to the qn dash limit n tends to infinity, both of them are the same. As a result, we can define the limit of x to the alpha when alpha is irrational. So that's why he is writing the definition on the next page. Now he can define, see, that's the definition. What is the definition? Exponentiation to a real exponent. Let x greater than 0 be real and let alpha be a real number. We define the quantity of x to the alpha by the formula x to the alpha is equal to limit x tends to n tends to infinity x to the qn, where qn is any sequence of rational numbers. This you need to, for now you have to remember it. But when you become an analysis student, you don't have to remember it. Now, because it is natural. If you don't know the meaning of 5 to the root 2, if somebody asks you, because you think, if you take a sequence of rational numbers qn with the limit 5 to the root 2, then you would think that you take such a sequence, qn is a rational number, qn converges to root 2, then 5 to the qn must be converging to 5 to the root 2. You think like that, and that is the definition here. It is natural, like even when we define that x is a real number and x to the 1 over n, how did we define? We said we took this set of all x greater than or equal to 0, such that x to the 1 over n, less than or equal to what, say, some letter, other letter. What, less than or equal to x. Supremum of this thing is x to the 1 over n. Because if you know how to calculate, so that long proof I gave. So you need to think, you need to feel that that's the way to define. For now, you have been here only not 3 months even. So both of you are good, but you could have been better than you are at this moment had we chosen a different book. Because from this book you are somewhat carried away to justify highly logical things. That is very good. That is very good, but every good thing has some kind of other side also, no? Let us check that this definition is well defined. He says, but however we have proved already it is well defined. First of all, given any real number alpha, we always have at least one sequence qn of rational numbers converging to alpha by the definition of real numbers. Secondly, given any such sequence qn, the limit of this thing exists. Finally, even though there can be multiple choices of the sequence, they all give the same limit by lemma 6.7.1. Thus, this definition is well defined, so that paragraph is actually not needed that much. If alpha is not just real but rational, so we have to be consistent with the, when you write the definition like this, so somebody may ask, if alpha is rational, there is a meaning, like 1 over n, x to the 1 over n, there is a, there is a different meaning. But for that also, suppose you want to find x to the 1 over n, n is greater than 1. Now two different definitions. That sup gives one definition, this one says another definition. So you have to prove that. You have to know that they are the same. If alpha is not just real but rational, that is alpha is equal to q for some rational q, then this definition could in principle be inconsistent without earlier definition of exponentiation in section 3.7, but in this case, alpha is clearly the limit of the sequence q and going on to infinity. So by definition, x to the alpha, you can write x to the q, limit of that is equal to actually x to the q. Thus the new definition of exponentiation is consistent with the old one. Same thing, because if that q is a rational number, you can turn the constant sequence q. So you know the meaning of x to the q. Therefore, old definition and this definition agree for when q is rational. It doesn't give a different answer. You got it, know what I'm saying? All the results of lemma 5.6.9 which held for rational numbers q and r continue to hold for real numbers q and r. We demonstrate this for the identity x to the q plus r is equal to xq times x to the r. It is the result when q and r are rational numbers. Now, that is the first part of lemma 5.6.9b. I guess the other parts are similar and left to exercise 6.7.1. The idea is to start with lemma 5.6.9 for rationals and then take limits to obtain the corresponding results for real series. So here he is proving that we know that if q and r are rational numbers, x to the q times x to the r is x to the q plus r. No, now if it is alpha and beta are two irrational numbers, we must be able to say that x to the alpha plus beta is x to the alpha times x to the beta. But this is true because you take, if alpha beta irrational, then you are wondering whether x to the alpha plus beta is equal to x to the alpha plus x to the beta. No, that's what he is talking about. However, there are sequences if there is a sequence alpha n is rational, converging to alpha, beta n is rational, converging to beta. Therefore, alpha n plus beta n converges to alpha plus beta, right? We know this thing, no? So then we have to prove that x to the alpha n plus beta n and this is what we need to prove. Alpha n tends to alpha, beta n tends to beta. We know this thing, x to the, alpha n plus beta n tends to alpha plus beta. Then, is this true? It has to be true. It is true. So, he is talking about that here. So that way, I don't know whether you have to write the exercise, prove the remaining of it. So, I guess he's going to have a hard time because you have to write all the details, but you need to prove everything once, even though it is kind of well. Now, proving this x to the alpha n plus beta n has a meaning because alpha and beta n are rational. Here x to the alpha n has a meaning, x to the beta n has a meaning. I suppose you can prove it. It will not be difficult. So, let's see the live on the 5.6.9b. 5.6.9. The bad thing is that to do the homework you need a lot of time. 5.6.9. Oh, 5 points. So all the, I guess x to the cube is positive, x to the cube plus r is x to the cube times x to the r. I guess we need to prove all of that, so it's tiring hard work. Not easy to write all of them, even though you understand. But another thing is that you really have to feel that these are correct before writing the proof. That comes by writing proofs. So that's why I say that you need to learn to write this. This book. It's from the book. He has written proofs. They are very good, but I suppose the proofs don't motivate you to write the proofs, because it is, as I told you, this epsilon, sometimes they use epsilon, sometimes it is not used. Analysis people have to be very familiar with epsilon, then sup, in, lim sup, lim inf, and lim, all of them. They are the things. I suppose chapter 6 is over, and real exponentiation part 2, it is only sweating. Subsequences, that is a very important one. As I told you, if you don't understand something, you need to tell me, because these are very, very important. And 6.4, there are a whole bunch of homework. Doing 20 problems per week is not, in USA you get only 5 problems per week. Here Dr. Rabat is asking me to assign you 20 problems. So I know that that's not easy, and that's why I guess he is asking more time. Before we leave 6 points, this chapter 6, are there other things that anything I would like, you would like me to explain? How to write a proof? Anything you are a little doubtful anywhere? On chapter 6, because I can do anything. Can you do, I told you, proposition 6.4.12 is very important. It has F parts, A, B, C, D, E, F. I guess I showed you how to do C, how to do D. I have pointed out to you that pictures don't give you proofs, but it kind of motivates you. It gives a sort of an idea how the proof should go. So anything you want me to, because we have some time left over, we can you prove everything on page 131? Can we go backwards here? 150 up. Anyway, can
one
you?
page up.
Eh?
1 page up. Only one more page up.
Okay, other things are not there. Can you prove this last one? Remember one thing, however, even if you are sort of writing to the style without feeling, that's not good. You have to have the feeling. Can you prove this one, for instance? Have you done it yet?
Not, we got up to 6 point.
No, it didn't come to.
Maybe
This one?
Maybe today, so.
6.4.13. Oh, not here. You are really behind in the way. That is something I don't like, as you said that. I am talking about things in chapter 6, you are struggling in chapter 5. So that's not good. And that happens because of, I guess, assigning tentative problem. I don't know the right thing. Anything you would like me to, discuss about from chapter 6, you can say anything. I will write on the board and do it here. 6.16, 1.6 problem, did you do it? Point 1.6, page 132.
Ah,
Eh?
ඒක සර් දුන්නේ ගන්න. ඒක සර් ලියලා දෙන්න.
මම දුන්නනේ homework අද සෙට් එකක් දුන්නා.
ඔව් සර් 6.1.6 එක සර් ලියලා දෙන්න කිව්වා.
ලියලා දෙන්න තිබ්බද? ලිව්වද?
ලාස්ට් පේජ් එක. අනිත් පැත්ත.
This one doesn't. Let's see. He has a proof. Would you like me to go through his proof?
yeah, I'm okay with that.
Is it okay?
It's okay.
Don't
If
mention
you
the name.
no.
Discussion.
No, it's okay, sir. But if you can go through it once and see if it is okay.
Okay, let's see. Let me read the problem. I remember this is a good problem. Let n going m to be a co-sequence of rationals. Write L is equal to me. What is this? We call it this capital lim formal limit. We have to show that n going on to converges to capital L. Let epsilon greater than 0. Assume for sake of contradiction that n is not eventually epsilon close to L. Use this and the fact that n is quotient to show that there is an integer capital N greater than or equal to m such that either n greater than L plus epsilon by 2 for all n greater than or equal to n or n is strictly less than L minus epsilon by 2 for the thing is here n is strictly greater than L plus epsilon by 2 for all n greater than n or n is strictly less than L minus epsilon by 2 for all n greater than or equal to n. So that is the thing. Again, show that. So, since let's say let n a and b a Cauchy sequence of Q. Prove let L equals formal limit a n and let epsilon 0 greater than 0 be arbitrary. Assume that a n income does not converge to L. Okay, you say assume that it does not converge to L. Since a n is Cauchy, there exists capital N belongs to N such that a n minus a L less than epsilon for all n L greater than n. From 1 and 2, 1 is a n does not converge to L. We can say there exists capital N greater than or equal to m such that L is formal limit of a n. Uses let epsilon greater than 0 be arbitrary. Assume that a n going m to infinity does not converge to capital L. Here next line is clear. Since a n is Cauchy, there exists capital N belongs to n such that absolute value of a n minus a L less than or equal to epsilon. And that is 2, first one is 1. Now, how you say from 1 and 2 we can say there is capital N greater than or equal to N. Because one thing bad is here in this line you are using capital N. It's Cauchy there is capital N here. Again you are writing there is some capital N. You should not do that because one get confused. No? Here capital N is used to show that capital N has the property that if you take any n and L, absolute value of a n minus a less than or equal to epsilon. That is the quality of capital N. Here you are saying from 1 and 2 we can say that direct is capital N greater than or equal to M. So when you say direct is here also capital N, is it the same thing? I wonder, you cannot write like that.
I'm assuming the same thing.
So from 1 and 2 we can say that direct is capital N greater than or equal to M, such that A greater than L plus epsilon by 2, A less than L minus epsilon by 2 for all. Isn't this something you have to prove? You are saying at once now. We can say 2 says it is Cauchy. Here he is saying there is a capital N such that simple N greater than L plus epsilon by 2 for all simple N greater than capital N O, A N less than L minus 2. But what I see is that you say from 1 and 2 we can say that. We can say they are at this capital N. So here, however, in the proof, because N is here, you don't have to say this way, because a capital N is already existing. No? When you say here, it is misleading. Now capital N is in the proof. When you, after this line, below this line, you can refer to this capital N. Again, you cannot say they are at this capital N.
So I wanted to converge 1 and 2 together. So converge on combine 1 and 2 together and write something.
And because when you are writing number 1 does not have epsilon or capital N or anything. Then you see what I am trying to say? Number 1, you see, assume that A does not converge to L. That's English only. You haven't explained that in epsilon or N or anything. Then you say this is Cauchy. Then you are saying right away from 1 and 2 you can say that. I guess you are saying what needs to be proved, and you can say we can say that. And that's the impression I am getting. Notice that N is Cauchy. Then by exercise 5.4.8 we have. I am wondering, did I do the problem? I do some problems. I am lazy doing these, but I think this is an important problem. 1? No, this is 2. This is 3. So I have spent a lot of time to do it. I guess you haven't proved what needs to be proved. You are saying, you say from 1 and 2 we can say. Better to say here, I get kind of confused because I don't like here you said they are at this capital N, again they are at this capital N. I object for that. I mean, what cannot agree. Because when you say they are at this in one place, if you say in a statement, you first say, say suppose you want to prove An is bounded and Bn is bounded, therefore An plus Bn is bounded. Right? You have tried to do it, that's a good thing. It doesn't matter you do it wrong, what matters is you try. Honest try. I'm going to show you something. Actually, my logic problems, maybe I didn't give enough then because we didn't spend much time with logic. Say, suppose An and and Bn are bounded sequences. We have time. Because I didn't start the next chapter because you are already behind. Yeah. Then suppose An and Bn are bounded sequence, then An plus Bn is bounded. Proof. Since An is bounded, there is M, say greater than 0, such that for each N belongs to N, not N, no? Z plus, oh, whatever, doesn't matter. Mod An less than or equal to M. Don't take it down because this is, I'm going to point out something. Again, since Bn is bounded, there exists, you cannot write same M here. You have to say there is M1, not the same guy. After that, of course, you can prove that there is the same M. But since Bn is bounded, there is M1 greater than 0 such that for it, because now M is already, you have said that it is there. Again, you cannot say here for it, N belongs to Z plus Bn less than or equal to. You cannot. These two statements are inconsistent because
M1.
when you, before you go to second line, capital M is already chosen. But you can prove that there is the same M. You are trying to say something.
Yes, sir. That should be M1.
Yeah, very good. You cannot write the same M. It is a different thing that you can prove it. Because we are writing, I mean, when you are doing, say, for instance, some homework, some there. A, let me write this in, converges to L. Bn converges to L. 1, 2. Let's not write L here. Nice letter A converges to A, Bn converges to B. You want to prove that A plus Bn given. This, you want to prove that A plus Bn converges to. This is not the precise way of writing, I'm just trying to get to the point only. Suppose you want to prove that. Prove that PT. Then you say since A converges to A, so let epsilon greater than 0. Since A converges to A, there is N belongs to Z plus such that for each N greater than N, or let me write it at the end, such that mod of N minus A less than epsilon by 2 for each N greater than N. This is true. Again, since B converges to B, there exists, you cannot write anything. You can, here what you can do is here you write N1, here you write N2, such that here is again N1, Bn minus B less than epsilon by 2 for each N greater than N2. Now you say let, oh, put, oh, I don't know, equals maximum of n1 and n2. When you take n is equal to maximum of n1 and n2, mod of n minus a less than epsilon by 2. If you take any n greater than capital N, both of them are true. So now you write let n greater than capital N. Right? Since n greater than n1, you have a minus a less than epsilon by 2. Right? Since n greater than n1, this is true. Also since n greater than n2, no, yes, n greater than n2, bn minus b less than epsilon by 2. Right? Because you cannot write the same n. Now you can say, notice that an plus bn minus a plus b, this is equal to an minus a plus bn minus b, triangle equality an minus a. Now can you see I have taken n greater than n. Now I cannot use this n again. If I am saying I have to refer to this first n, bn minus b. This is less than epsilon by 2. This is less than epsilon by 2. This is also less than epsilon by 2, which is equal to epsilon. So now I have to look, hence, for each n greater than n, an plus bn minus a plus b less than epsilon. So, limit of n plus bn is equal to a plus b is proved. When you say like this, you run into problems. Because you said there is capital N greater than n belongs to n, no? Then you don't again say there exists n greater than or equal to m. You know about capital N already. You see, do you follow this one? I think I don't do all the problems. I told you I do some problems in the diary. Next day I had to bring the diary. Sometimes I cannot remember how I did it. However, I have spent this page and half of the next page also to do it. Because that is the reason, because for some problems I write the solution. Here I have written 6.1.6. What is this? 5.4.8. I have assigned. I have done that also. What else I have done? I have written that. I couldn't copy from the diary. So I think there is a question, because here actually you have to prove, no? You did this one?
Yeah, I have a different sketch of it. So on the way they have instructed.
You did in a different way.
Yeah.
Let's see. Oh.
Give it up.
L is equal to limit an capital N, no? And let epsilon greater than 0 clearly. L equals, you are saying again it clearly, no? Why? First line you wrote L equals formal limit A. Again you are saying clearly it is equal to
You can limit capital L inside. Formal limit.
No, here you have written the same thing.
No, two that up there it's AN, down there it's capital
Ah,
L.
oh, clearly L is equal to constant sequence area. Then A and n going to infinity, and this R,
Equivalent.
I don't see it here.
No, you have to.
Equivalent. Since A is An and going on to infinity, and L are equivalent. You said why? Because they converge to clearly L is equal to this thing. You have two different sequences, formal limits are the same. Then they are equivalent. Have you proved it? Yes.
By
No?
definition.
By definition. Equivalent. Let m greater than or equal to 1, such that for each n greater than or equal to m, a not of n minus l less than epsilon. Right. Because a n converges to.
No, because they are equivalent
Isn't that-
sequences. Because
But-
they are equivalent sequences. The AN sequence and the L sequence. They are equivalent, so there must be an they are eventually epsilon cross.
Plus a n and then 1 to n converges a. Is this good?
Yeah, that's the problem.
I don't know. So you have this thing, and he gave me the solution.
No,
or
I
it
didn't.
had written?
I'll give it next.
I kind of wonder. You say A converges to thusly means you may, I cannot say you are right, but I cannot say you are wrong either. Because you know, one problem I have is this in this, this with the book is that then when you say something, he has equivalent definitions, quite a lot of things I cannot remember what is, because I have to forget what I know. That's the reason this whoever graded could not continue to do so, because he has to go through the book just because of his has done. Anyway, you write here, you said L is equal to I guess if you are right, it's a very good solution. If you are wrong, it doesn't say anything. So I wonder. So next day when you come, can you write this thing on
I'll
this?
write it down right now.
Yeah. I want to take it home and see.
Sir, can you check out the below part of my proof?
This is a contradiction.
It is a kind of
Therefore, we can prove that A converges to L, hence converges to limit. Here, notice that A is quotient, L is equal to limit. Then by exercise 12.4.8, we have this is a contradiction. If your solution is correct, even I, because what happened to me was I wanted to follow the
Yeah,
method.
yeah.
No? So, but you have thought independently, that's very good. And if you are correct, it is like it's a very good solution. If it is correct, if it is wrong, of course it is wrong. Can you see? I could not listen to me. I could not say your solution is correct or wrong because I don't know what is in these chapters. Can you see what I'm saying?
Yeah.
That's why that grader cannot grade.
And here are
So I will show you after he gives his solution. If he is correct, it is a very good solution if he is correct. But I wonder whether it is correct, so I will have to go through. I want a copy of it, solution. Buddha, again I gave you 2 problems graded to you, no?
Yeah.
I have written something by red pen. Go through it. If you don't understand, ask me. It's simple. Do you notice that I have difficulty in looking at the solutions? I don't know what you know. I myself don't know what I know from the first 12 chapters. I am confused.
The thing is, when we do the previous problems,
Yeah.
and we know that the facts that after that, so in our mind we know that
You know it is.
it is, and sometimes we use some properties after that chapter.
They are rude. Yeah, that's not good. Now I couldn't say his solution is either correct or wrong. So I have to take his solution, go back to the book and see whether he is right. Anyway, after I can stop at 110. No? I will show you. I try to follow his hint. This is not a hint. What is it? He says that? No. Hint is not used in this book language. These problems are good. But the thing is that we are not in that boat. No? As you said, here you have to do, here you are using. That is the thing. Oh. Now anyway, you got my point, no? You cannot try. When you say they are like this, the thing is that it's bad that you guys did not have enough time to go through my logic book and so these are discussed over there. I proofs where you do mistakes by using the same name. Thank you. If your solution is correct, actually, it's a method that he hasn't seen.
yeah.
I could not say it because I was trying to follow you. Actually, to tell you the truth, I don't know what do I know from this book, from the first 5 chapters. Because all are new, that's all. Anyway, I have done a couple of problems, I guess. Not enough time, but let's go through quickly. So here actually, the question here is if formal limit and actual limit are the same, no? That's the thing. So suppose A is a Cauchy sequence of rational numbers, then A n going from infinity converges to lim A, no? if it is a co-sequence. In my proof I have written proof. Sometimes I tell the students, okay, I did half of the thing because I wrote proof, no? You do this. Right, okay, I say right, L is equal to lim n tends to infinity. Assume it is not the case that I am saying assume it is not the case that it is not the case that A in n going infinity converges to capital A. I am going after a contradiction. Thus, so but later, thus there exists there exists an epsilon 0 greater than 0. If A n does not converge to L, there is an n greater than 0 such that A n equals m to infinity is not epsilon 0 close to capital N. Right? Capital N. Since n going up to infinity is Cauchy there it is capital N. So I can write capital N here, it is not used before. Capital N greater than or equal to simple n, it is with the sequence such that for each n comma k greater than or equal to capital N mod of A n minus A n where am I? A minus A k I have that n k A minus A k less than this epsilon divided by 2. Right? Thus, for each simple n k greater than or equal to capital N, we have minus epsilon 0 divided by 2 is strictly less than A minus A k is strictly less than capital epsilon 0. Like this, no? The same thing. I call it star. This line is star. Since A n going 0 to not 0, m to infinity is not eventually epsilon close 0 close to capital N. It is something I said earlier, no? A n going m to infinity is not epsilon 0 close to L. There it is k greater than n. A greater than capital N such that AK minus L is greater than or equal to epsilon 0. Right? Since this sequence is not eventually epsilon close to L, after capital N there must be at least one integer, here like this. So, AK minus L greater than equal to epsilon 0 O, AK minus L less than or equal to minus epsilon 0. Yes. No. Mod x less than 2 means x lies between. Mod x greater than or equal to 2 means sometimes I get confused. Either x greater than or equal to 2 or x less than or equal to minus 2. That is the have I done it correct here? So AK minus L greater than or equal to epsilon 0. Oh, right. This one is correct. Right? Minus epsilon 0. So now what do I say? Since the sequence is not epsilon close to L, after capital N there is this guy, such that AK minus L greater than or equal to epsilon 0. Now, this K, again, I cannot use again, so I write AK0 in my solution. I have not written, but what do I am trying to say is that when I say there is K0, thereafter that you, if you write there just direct is K, you cannot use K thereafter, because this is a particular K now. K0 is greater than N and AK0 minus L greater than or equal to. So this one and this line are the same. Right? Now I say case 1. Assume that epsilon 0 less than or equal to AK0 minus L. Right? I am assuming that that's my case 1, because here no variable thing. K0 is fixed now, capital L is fixed now, epsilon 0, all of them are variable letters over there. So I call it this guy is 1. Now what is the property of this AK0? K0, either AK0 minus L greater than or equal to epsilon 0 or AK0 minus L less than or equal to minus epsilon 0. Right? Now let N greater than or equal to N be arbitrary. I took anyone, anybody. Right? From star, I say there is one star over there. We have, what do I have? Minus epsilon 0 by 2. Now here, Nk are variables. And I can substitute, this is true for even K0, because K0 greater than or equal to N. We have minus epsilon by 2, strictly less than An. I took N greater than or equal to N, minus AK0. Right? From star we have this line. Then if you do 1 plus 2,
You have a name to it.
I have excluded 2 things. 1 from 1 plus 2, what do you get? You are adding this one and this one. When you add these two, you get epsilon by 2.
Strictly greater than A.
Strictly less than minus AK zeros cancel, A minus L. Right? And hence, L plus epsilon 0 by 2 is strictly less than A. Right? Now this N is varies. So this is arbitrary, simple and greater than or equal to capital N. Thus, for each N greater than capital N, L plus epsilon 0 by 2 is strictly less than A. Isn't that what something he has asked to prove? No? I have now proved that for all N greater than, for each N greater than capital N, this is something he has asked us to prove. Right? Then again, I have asked you to do 5.4.8. Yeah, I have done it also, but good. Oh, good great grandfather. Then from exercise 5.4.8, it follows that. If you do exercise 5.48, then from exercise 5.4.8, it follows that if you do that exercise, L plus epsilon 0 divided by 2 less than or equal to lim A in formal limit intention. Right? Since epsilon 0 by 2 greater than 0, we have lim capital A in lim capital lim is strictly greater than L. Can you see? Now I was going to prove lim capital A is equal to L. Somewhere I assume it is what the case that this guy converges to L. Then I am getting formal limit also strictly less than L. Right? This is a contradiction. This is a contradiction. Now this is what is expected, but if his solution is correct, that is much better. In your case, you haven't seen the difficulty. That's why I say, if you write correctly, only you will see the best part. If you don't write, if you just pass places, you will not. See, case 2 again I have. No, I cannot do it today. Case 2. Case 2 again this way. One thing, not enough time. Yes. Bukan kita. Solution. But I have to give you the other day.
Then I'll take it.
You take this part. Can you see, however, this my proof? Because you are doing a mistake then. When you say direct is N at one place, you shouldn't say again direct is N. You should say that there is M or some other letter. Because we don't know whether both are the same. That will lead to contradictions. But this one is clear, no? This part, this much. One thing by the way, had he not given this as exercise, it would have been very difficult problem to think like this. Because he has given it, I tried to prove it. I mean, it's simple, but I was led to go through this because of what he has asked. So next day when I come, I will do the other part also, just take the copy in here. And I have, if your solution is correct, it's a very good solution. If it is incorrect, I won't say anything about you.
Implies.
I wanted to finish the whole problem, but didn't have time. Can I start the meeting? Yes, let's go.